Welcome to the Explainer. You know, there are these truly apocalyptic objects out there in the universe. We're talking absolute engines of destruction, menacing, mysterious, and completely invisible. Yet they possess a kind of power that's almost beyond imagining. I mean, they can swallow an entire star completely intact, spew out massive jets of matter at near light speed, and even slow down the flow of time itself. For decades, scientists thought they were just a bizarre mathematical anomaly. They were just this outrageous idea discovered on paper with a few squiggles of a pen, an idea so wild that even Albert Einstein absolutely refused to accept them as real. So, what actually happens when gravity literally breaks the universe? Today, we are exploring the most mind-blowing, reality-shattering objects in the cosmos. We're going to travel to places where everything you think you know is completely challenged, and where the very fabric of space and time is stretched to its absolute breaking point. Okay, let's dive right into this. Section 1. The ultimate cosmic mystery. What exactly is a black hole? Right off the bat, despite the name, they are not empty voids or holes in space. They're actually massive, massive concentrations of matter packed into infinitely tiny spaces. Just imagine an object with virtually infinite density, where all of its mass is crushed down into a single microscopic point. That extreme concentration creates a gravitational pull so intense that absolutely nothing can escape its grasp. But we really need to clear up a few sci-fi myths here. They are not wormholes acting as magical shortcuts to other dimensions, and they definitely aren't cosmic vacuum cleaners maliciously sucking up everything in their path. Actually, think about this. If you replaced our sun with a black hole of the exact same mass, the planets would just stay in their exact same orbits. Nothing would get sucked in. From a safe distance, a black hole's gravity acts exactly like any normal object. Section 2. From math to reality. To really understand these things, we have to look at how Albert Einstein defined gravity. Back in 1915, Einstein proposed that gravity is actually the bending of space and time by mass, kind of like a heavy bowling ball sitting on a trampoline. Well, just weeks later, picture this. It's World War I, and astronomer Karl Schwarzschild is literally calculating artillery trajectories on the Russian front. Amidst all that, he finds an exact mathematical solution to Einstein's equations. He proved that if you concentrated a star's mass into a single point, it would create a boundary of no return, a sphere where time just stops and light gets trapped forever. It was later described by physicist David Finkelstein as a perfect unidirectional membrane. Basically, you can check in, but you can never, ever check out. Einstein was completely astonished. It actually took decades for physicists to believe these mathematical weirdos existed in the real world. From Schwarzschild's exact proof on the battlefield in 1916, it wasn't until 1967 that physicist John Wheeler popularized the actual term black hole. Then, in 1971, using X-ray astronomy, we finally identified Cygnus X1 as the first real candidate. And finally, exactly a century after Einstein's theory, 2015 brought the ultimate mic drop, the direct physical detection of two colliding black holes. Section 3. Birth of a stellar corpse. Let's shift gears and look at how these strange objects actually come to exist. Imagine the violent death of a massive star, say one about 10 times the mass of our sun. A star's whole life is basically a constant, intense tug-of-war between fusion and gravity. By burning hydrogen, the star creates this immense outward pressure that perfectly balances the inward crushing force of gravity. But here's the catch. Massive stars eventually fuse heavier and heavier elements, all the way up to iron. And iron is a complete dead end. It takes more energy to fuse iron than it gives off. So without that outward pressure, gravity instantly wins the tug-of-war. Trillions of tons crash inward in a fraction of a second, blowing off the outer layers in a massive supernova explosion. Meanwhile, the core is crushed down into an infinitesimally small dot. And just like that, a stellar corpse is born. Surrounding this completely dead core is what we call the event horizon, a boundary of absolute pure darkness. Because the gravity is so incredibly extreme there, time itself warps. If you were safely far away watching a spaceship approach this boundary, you'd see it move slower and slower. It would literally appear frozen in time right as it reached the edge. But if you were the one who actually crossed that event horizon, well, the reality is visceral and, frankly, terrifying. Because the gravity increases so drastically the closer you get to the center, the pull on your feet would be vastly stronger than the pull on your head. You'd be squeezed horizontally and stretched vertically into a long, thin noodle. It's a very real scientific process brilliantly named spaghettification. Ultimately, you disintegrate into fundamental particles before ever hitting that infinitely dense singularity at the center. Section 4. Monsters shaping the galaxies. We're moving from stellar corpses to colossal behemoths that change everything we thought we knew. Now, what's really interesting about this slide is the sheer scale. A standard stellar black hole? Sure, it's terrifying, but it could basically fit inside a city. But look at those supermassive and ultramassive classes. These are absolute monsters, ranging from millions to tens of billions of times the mass of our sun. The largest one we've observed, called TON 618, tips the scales at an incomprehensible 66 billion solar masses. A single dying star simply cannot create something that impossibly huge. And guess what? We happen to have one of these monsters living right next door. Astronomer Andrea Ghez won a Nobel Prize for tracking stars whipping around the absolute center of our Milky Way galaxy. These stars are moving at mind-bending speeds of up to 10 million miles per hour. That essentially proves there is a dark mass weighing 4 million times what our sun does, silently sleeping right at the center of our galactic neighborhood. So we now realize that supermassive black holes anchor virtually every large galaxy out there, and they actually grow in a sort of symbiotic tandem with their hosts. When a central black hole feeds, it blasts out a tremendous amount of heat. That heat warms the surrounding galactic gas and effectively quenches the formation of new stars. So in a very real, literal way, these black holes are dictating the ultimate structure of the galaxies they live in. Section 5. Listening to the universe. This was a monumental shift in astronomy that changed the game forever. See, because black holes completely trap light. For about 400 years, basically since telescopes were invented, we could only spot them by watching how they mess with the visible stars and gas around them. Almost everything we knew about space came from analyzing electromagnetic energy, like visible light, radio waves, or X-rays, but a revolutionary experiment offered us a totally new way to look at the cosmos. Enter gravitational waves. Predicted by Einstein a century ago, these aren't light or sound. They are the actual physical squeezing and stretching of the fabric of space-time itself, rippling outward from the most violent events in the universe. In September 2015, the LIGO observatories picked up a tiny, tiny chirp. But that chirp was the ringing of the fabric of reality. Over 1 billion years ago, two massive black holes swirled together and slammed into each other, releasing an explosive blast 50 times more powerful than the light of all the stars in the visible universe combined. I mean, think about that. That invisible wave of gravity traveled at the speed of light for 1 billion years. It washed over the Earth while supercontinents were still forming, zoomed past while dinosaurs roamed, and finally struck our detectors in 2015, proving beyond a shadow of a doubt that black holes can merge and grow. Section 6. The future of black holes. Let's talk about the ultimate cosmic endgame. So, we've seen how they form and how they shape our galaxies. But what happens to these devouring beasts over, say, trillions of years? Right now, in the universe's current era, black holes are growing. They feed on gas, strip apart passing stars, and collide to become vastly heavier. It almost feels like one day they could swallow absolutely everything and just rule a dark universe. But quantum theory predicts a really strange twist. Physicist Stephen Hawking proposed that over untold trillions of years, long after the very last stars have burned out, black holes will slowly leak energy back into space. As they emit this Hawking radiation, they will eventually just evaporate and fade from reality entirely. These things represent the absolute extreme of nature. They are the violent, reality-breaking sculptors of our galaxies. And yet, even they are destined to evaporate into nothingness. It really makes you wonder, if black holes truly do consume all the universe's matter, only to slowly vanish themselves over trillions of years, what exactly is left behind? It's a question that completely pushes the boundaries of science and honestly leaves you in awe of the ultimate fate of our reality.